behind. We call it implicit differentiation as opposed to explicit. Those are the two terms. We've been doing everything as explicit functions, explicit differentiation. An output variable is written as a function of the input. For example, if I give you, let's say, x squared plus 2x plus y minus 4 equals 0, can you write that as y equals? Sure. Yeah, you can do that. I mean, this is nothing more than Algebra 1 type of stuff, so you'd probably say that, okay, y, whoops, not the way I wrote it. Hang on. Give it to you wrong. That's supposed to be an x. There we go. So you would say, well, that equals 4 minus 2x minus x squared, for example. Okay? So we can write things explicitly, and if I ask you to take the derivative, you'd say, well, no problem, dy dx. Now, when we say dy dx, what exactly am I identifying with this notation? This identifies what again, down here? The input variable of the derivative, and also of the function I'm using. What does the y represent? The output of the function I'm using, okay? So we'd have, let's see, 0 minus 2 minus 2x, or simply negative 2 minus 2x. No problem. We can do that in our sleep now. This is the quiz material that we're going over. However, implicit, I guess if you have nightmares maybe, but okay. Implicit means that I cannot do that very same thing. For example, if I give you x squared plus 2xy plus y squared equals 3. I challenge you to write it as y equals. Now, if you look at that, you say, well, that's no problem. I can say, start some work here. I can say, well, it's 2xy plus y squared equals 3 minus x squared. Okay, I can factor out a y. Okay, so I have 2x plus y. Uh-oh, I see a problem already with this. Because now, how am I going to get rid of, how can I write this as y equals, when if I try to divide by this, I have a y term over here now. So this is the type of problem where we end up having having a need. We want to find the derivative, but it's just impossible to use what we've been using because I can't write it as y equals. Impossible to do that. Okay, so this brings up then implicit differentiation. We're going to have to look at something like this as, if I want to find the derivative with respect to x, I am going to use, and every time I see an x in my work, in my term, I'm going to be just fine. But if I have something other than x, for instance, if I take the derivative with respect to x of y squared, I've got a problem. Because this says x and that says y, and in my book, those are not the same letters. Okay? Not the same. So I've got to do something different. Well, what we do is, I look at this as a composite function. It's a very simple composite function, but let's suppose that I could write y as some value. Not to be confused with what we have up there, okay? If I could take this y and write it as y equals, and I have something over here, I don't know what it is, I have something over here, then I would have this quantity squared, I would have a composite function. I would have the inside function is y, and the outside function is take the result of that and square it. And so when I look now at this term, I have to realize that that's not the simple derivative I need. I'm going to take the outside function derivative, just like I did in section 2.5, and that would be 2 times y to the 2 minus 1 power. But now I must take the derivative with respect to x of the inside function. So we can say this is the outside function, this is the inside function. And my answer for this would be 2y dy dx. This term here, its derivative, is equivalent to this right here. Because I don't have the same letters, I treat this as a whole function of itself. I don't know what y represents. It could be anything. But it's a function within the function of squaring. How are we doing? Did you follow that? I look around and I see blank stares. Okay? So we're going to try this again. Here we go. Another problem. Actually, well, yeah, another problem here. We're going to do implicit differentiation on this. Now, first of all, I see a quotient. Do you? Right, there's a quotient. So I got to use the quotient rule. So to start with the quotient rule, I'm going to take the denominator times the derivative with respect to x of the numerator minus the numerator times the derivative with respect to x of the denominator, all of this divided by the square of the denominator. But now this one's a little different. You see it says equals 1? What we did was we took the derivative with respect to x of this side, and you know the rule. What you do to one side of the equation, you must do to the other. So I'm actually going to take the derivative with respect to x of that side also. And it happens to be 0. Derivative of a constant is just 0. Okay, so this one now, let's put this up here. This is the quotient rule. And I call this line right here, this is one of my lines of intent. I use that in the quiz. Line of intent, meaning this is what I intend to take derivatives of. This is my intention to do, the derivative of this and the derivative of that. So I'm intending, I haven't done it yet, but I intend to now. So actually this would also be a line of intent. And this would be showing a line of intent. Okay, so let's see, I've got 2x minus y. The derivative of x plus y. Let's break it apart. What's the derivative of x with respect to itself? 1, okay. Plus, what's the derivative, I'm going to write it out, the derivative of y with respect to x? And that's just simply, go ahead, Addison.
0.
No. No. What? No. Someone said it. Who's? Say it louder. Not. I don't want to say over. I don't know how to over. Yeah. We actually in the notation piece we just say dy dx. Remember? This is nothing more than dy dx. This is why that notation is so important to understand. What I've got is I'm taking the derivative of a quantity. Didn't I take the derivative of this quantity when I wrote it this way? Look at that. If I write it this way, don't I have the same thing? The derivative of a quantity, x plus y, the derivative of a quantity, y, with respect to x. But we often, because we do this so many times, we don't put those parentheses there. We just say it's dy dx. But I did the very same thing here as I'm doing up here. I'm putting it inside parentheses, and that's the quantity, that's my output actually of a function. The function is x plus y, its output is x plus y, and I take its derivative. Okay, well, we'll come back, we'll keep working with that. Minus the quantity x plus y, and what happens over here? I've got a function, 2x minus y. I got an output of a function, 2x minus y. What's the derivative of 2x? It matches, right? X and x match. Minus, but here again, does the y match the input variable of my derivative? No. I treat it as a separate function, and so I have the derivative with respect to x of y. Again, I could just write dy dx. Let me get this out of the way, though, because we're not done with this side. All of this divided by 2x minus y quantity squared is equal to 0. Okay, so let's see. I've got 2x minus y times 1 plus dy dx minus the quantity x plus y times 2 minus dy dx, all of that divided by 2x minus y quantity squared set equal to 0. What am I trying to do with this problem? Go to the top again. What did it say? Yeah, we need to determine an expression for dy dx, for the derivative. So, how close are we? Can I solve for dy dx? Now let's see. If I multiply this together, I have 2x plus 2x dy dx minus y dy dx. That's all for this. I'm just multiplying those terms out.
Can you break that down?
Yeah, 2x times 1 is 2x. 2x times dy dx is 2x dy dx. Negative 1 times y, negative y times 1 is negative y, and negative y times this is negative y dy. I just used the FOIL on that. Minus, I'm going to put this in brackets here just to make sure that I don't lose anything. First terms would be 2x. Outside would be negative x dy dx. Inside, 2y, and last term to be negative y dy dx. All of that divided by this, set equal to 0. Again, I'm trying to solve for dy dx. Believe it or not, I think we're going to get there. Okay, so if I take away the brackets, can I do that without rewriting that whole numerator again? Can we keep track? This is negative, this is positive, this is negative, this is positive. Okay, so I'm going to have, let's see, here's a dy dx term, here's a dy dx, here's a dy dx, and here's one. So I think if I do this right, I'm going to have a 2x minus y plus x plus y dy dx plus 2x minus y minus 2x minus 2y, all of that divided by 2x minus y quantity squared set equal to 0. I took all the dy dx terms, collected them, factored out a dy dx. I have a 2x minus y, we change the sign, plus x, we change the sign, plus y. Now do you think we can solve for dy dx? What's an algebra step right now we need to take? Say that again. Oh, do I have two x's that can cancel? I sure do, don't I? I didn't see that right there. Thank you. I was focusing on something else. With that in mind, I could also add those together, couldn't I? And get negative 3y. Okay. I was focusing on something else, though. What else can we do? Because you're absolutely right. We can do that. So supposing that we collect these together and get negative 3y, then what? my time?